Okay, everyone can hear me? And also the screen. Let's see. Okay. So, in the second, I hear myself. Now I think it's better. Okay. So, the second session, we start by overviewing what we discussed in the first session very briefly, and then we dive into the mathematics of Riemannian geometry and its close relationship to connections, affine connections, and we would try to solve an EM problem, estimation maximization, and we show how information geometry would help us, would give extra structure on the space of probability distribution that helps us to optimize this problem. So in the first session, we discussed what is information we're dealing with. More importantly, we discussed how considering KL divergence and its second derivative estimation would give rise to our inner product on each point, which later would help us define Riemannian geometry. Also, we discussed about the second kind of distance we could go with, Wasserstein distance, and what is the relationship the two between KL divergence geometry and the Wasserstein distance geometry. And lastly, we discussed about this special example, which we tried to optimize an estimation problem, the following estimation problem where we observed n data and we want to fit the best, quote unquote, normal distribution over these 100 points using the two gradient descent methods, one with leveraging the geometry or curvature of the space induced by KL divergence, and one with Wasserstein distance. As we saw, the intermediate distributions resulting normal gradient descent would be as sketched here. So if we want to optimize from this to the resulting distribution, the trajectory of the distribution we're observing is as follows. But if we consider the geometry, which would essentially go through the distributions in the meantime that have less, that have larger variance, they would converge much faster. So this was the whole session one. So with geometry, we want to take over the optimization process and make it faster. And with information part, we are estimating. So information geometry is the method of estimating faster with leveraging the geometry over the probability distribution. Everything we discussed in the first session was a little vague. We did not go into the details of mathematics behind Riemannian geometry as well as information geometry. So in the second and third session, we would try to understand the essentials of Riemannian geometry. Of course, this course is not meant to be an introduction to Riemannian geometry. There are lots of online courses and notes and books. You can get more and more of Riemannian geometry, which is a 200 years old field. But I would try my best to talk about the essentials of Riemannian geometry we need in order to tackle the problems in statistics and later see the usage of them in both machine learning and finance. So before I start the second session, if anyone has any question from the first session or the recap, I would be more than happy to discuss, and then we go into the mathematics of Riemannian geometry. In the meantime, I check. Okay, we're recording. Okay, so if there is no question, we continue. Okay. Okay, so in the second session, we would start at first by going through a fitting Gaussian mixture model. We see how both maximizing likelihood estimator would not give us a meaningful result, and also other heuristics. So we need the algorithm of estimation and maximization, which many of you have already seen. And then throughout the second session, we would develop the essential mathematical tools to review this whole estimation and maximization algorithm through the lens of information geometry. So let's start with the problem. Consider n data points observed, and we know they're from a Gaussian mixture model. For simplicity, consider they come from two Gaussian distributions, but we don't know which data is coming from which Gaussian distribution. Now, if you try to optimize the maximum likelihood estimator, because you don't have access to P1 and Pi2 in this example, this is not tractable. One heuristic could be to assign randomly each data point. For example, I start with x1 and the first half, I would just randomly decide they're coming from the first distribution, and the other half coming from the other. I optimize, then I have enough tools to optimize mu1, sigma1, mu2, and sigma2 based on this model I have, which is essentially maximum likelihood estimator. And then I would reassign each point to each distribution and would do the same. But as you can see, the assignment of each point to either distribution 1 or either distribution 2 is a task of not mathematically correct way. So when we start from, I'll show the mixture model as pi alpha. So I start from pi alpha naught, which is random assignment of each point to each either one or second normal distribution. Then I would maximize the likelihood of mu1 sigma 1 and mu2 sigma 2. And then using these, I would reassign each point to another. But the problem here is how to do the second step. We already know the first step, which is just maximum likelihood estimator. So this is the famous EM algorithm, which you estimate and then maximize the likelihood. It is as follows. You start with the log likelihood of mixture of Gaussians with some weights which you compute. So each point has Ri1 probability to go with to come from the first distribution and Ri2 to come from the second distribution. Then we iterate through Ri1 and Ri2 to compute and converge. This is the estimation part. Based on that, you do the maximize likelihood, which is essentially the same, and then you repeat it. Compare this to the naive algorithm of randomly assigning each point to each normal distribution and then trying to optimize this. The second approach does not leverage any knowledge in the first approach. By using R sub ik, we're leveraging the likelihood of each point. In the first session, we discussed how the M step here is optimizing the path that goes from the least likelihood distribution to the most likely distribution over the data points. But what is the estimation part we're doing? So just to show you the difference between the two algorithms, as you can see, the left one is EM and the right one is some random initialization and going randomly from that part. This setup is clear. Anyone has any questions for the setup? Okay, I hope everything is clear. So now we want to see, let me just sketch. So we start, again, consider this as the manifold, which is parameterized by mu1, sigma 1, mu2, sigma 2, and essentially p1 and p2, pi 2. So we start from this manifold. The second step, the maximization of likelihood we're taking, we already know. This is the least information loss. Okay, I'll discuss that. So in the second part, which is the maximization step, we are taking the geodesic, which is with respect to Riemannian metric we developed in the first session, to take that geodesic and create the maximum likelihood estimator. But we started from some random pi1 and pi2. In the estimation part, we are doing this thing, which is strange. Why to go with probability of each model coming from each? So instead of hardly assigning each data point, so data point 1 is 100% coming from the first distribution, and then I would iterate through all possibilities. Instead of doing that, I start from a soft estimation. So there is a 0.9, I start from this. There is 0.9 probability that data 1 is coming from the first distribution, and there is 0.1 probability that data is coming from the second distribution. So, and it's given by this formula. We already know why these things are true, because they're maximizing the likelihood. But where does this formula come from? This is just some heuristic we're using instead of hard assigning each point to different clusters to soft assigning points. So this is the question. Is there any geometry, any path we're taking through the space of all possible mixture models of two normal distributions that we're taking, that if we find the geodesics over that distribution, it would result into this? That is the question. So in the just to make it clear that what does R sub ik calculates, it calculates the probability of data point I, the likelihood of data point I coming from distribution 1 versus coming from distribution 2, the normal distribution 1 and normal distribution 2. Hadi, is that clear? Okay. So also, the other thing I wanted to mention here is that, as you can see, in this estimation problem, you cannot leverage maximum likelihood estimator in the first part, because there is no smooth thing to go through, because PIs are not coming from a smooth or any kind of likelihood that we can maximize. So what's the ES step is doing? That's the core of this, and the next session we want to discuss and develop the tools to see what this algorithm essentially do in the language of information geometry. Okay. Now we are going to dive into the definitions and mathematical formulations of a smooth manifold. So, as we discussed in the last session, a manifold is a generalization of Euclidean space. So, given Rn and charts, if there exists coordinate charts which are homeomorphisms, and we assume that they're smooth, so we can differentiate them as much as we want, then this is the smooth manifold. So it's just a generalization of Euclidean space. Then, as we saw, we need to discuss about vectors to talk about angles, because we're talking about geometry, and geometry is nothing but calculation of angles and distances. So in Euclidean geometry, you could, at each point you have vectors, and you can compare them easily. But in the smooth manifolds, we need more structures to be able to discuss about each vector. So that is the tangent vector space. So at each point of our manifold, example as this, consider the tangent space TPM as the space of all vectors. This is essentially gluing Rn into that point, and we call this the tangent vector. And as you remember, the basis of this vector space is given by x1, x2, xn. For example, if I have a circle given by cosine of theta and sine of theta, then the tangent vector is given at each point by something like this. So at this point, which is 45 degrees, if I want to show the space of all tangent vectors glued at point here, I should write it as the following. And then I have x So as you can see, the point is glued to the vectors are glued. So it's not practice. It's not, we cannot add or subtract vectors of this point to another point. There is no relation between the tangent spaces of different points. We are just given different points and different tangent spaces. Then that is the place that the whole geometry thing come up. So as you remember, so this is essentially, again, a representation of each tangent vectors given the basis. And then we assume everything is smooth. So we can talk about the vector fields over our manifold. So given each point, the vector field gives you a tangent vector to that point. And all we need is for the smooth vector field to be smooth. So with differentiation of the point, the vectors are getting closer so that we can differentiate the vectors as well. And then we define the Riemannian metric, which is essentially the definition of inner product between two vectors. And the great thing that enables us to use Riemannian geometry on the space of the whole probability distribution is that the inner product is dependent to the point at each point. So given two vectors, we want the Riemannian geometry to give us the inner product between two vectors. And essentially, because we have n by n vectors, so the Riemannian metric is given by an n by n matrix. So is that until here we discussed essentially what we discussed in the first session. Now, with this inner product, generalization of inner product, we are now able to define the norm of a vector and also the angle between two vectors. Yes. So until now, we discussed about smooth manifold, tangent spaces, and Riemannian metric. But the way we can go further from here is that, as you might ask, so at each point of our Riemannian metric, we have a tangent vector here, and we have another tangent vector here. So what's the relationship between vectors in different points? One might say, okay, we have access to inner product at each point, but that does not give us any clue how we can go from one tangent vector to another one. So we need to develop tools to be able to move, as we can move through this curve from point P to point Q, we need to develop tools to be able to move the tangent space as well from point P to point Q. So that's where we're gonna discuss about connection. So as we saw, in Riemannian geometry, we know how to measure lengths and angles, but how do we compare vectors at different points on a manifold? Consider you're holding your compass and you're moving alongside the Earth. The compass is always showing you north. So when you move, the north, which is the tangent vector at the point you are on Earth, moves as well. So how we can mathematically come up with a definition to show that if I move, I want the vector to show the same thing. So we need a way to define how vectors change along curves. In information geometry, consider the manifold of normal distribution, for example. If we are able to move tangent vectors, then consider tangent vectors as the push you need from going one normal distribution to another normal distribution. So if we are able to talk about changing the tangent space, we can take gradient and move alongside the gradients. Okay. Now we need to define affine connection. So connection, which we are restricting ourselves to affine connections, are essentially given. So starting from, again, consider I have two manifolds. I have one manifold and 2 points. I have point P and point Q. So here I have a vector field. I show it with X. And then here I have a vector field Y. So Y is a vector field, and I can look at Y at point P, X at point P, and Y at point Q, and X at point Q. So the connection we define is to tell how the second vector field in here, for example, y, changes in the direction of x. So if I move my curve, if x is in this direction, if I move in this direction, which is the direction of x, how does the y vector field changes? And I'm restricting myself to all connections. So given a vector and another vector, you want the affine connection to give you another vector. So it's a type 3 tensor. Out of all those functions we can imagine, we're restricting ourselves to the linear functions that we call affine connection. So as you remember, so given if I can define my connection on the basis, like consider you want to define a linear function. All you need to do is to find its image over the basis you have, because affine connections are linear functions, as I have mentioned here. So all you need to do is to find the affine connection on the basis you have. So consider the basis we talked about, which was C1 till Cn. So I need to calculate the affine connection of changing the jth basis with respect to ith basis. And that is given by a linear function. So in order for you to have an affine connection, all you need to do is to have access to n to the power of 3 number of float numbers. So you need your affine connection to be smooth and everything. So these Christoffel symbols, which we show by tk sub ij, need to change smoothly with respect to point P. And essentially, I will calculate how we came to this calculation. So you are going to, x could be represented by summation xi, ci, and then y could be represented by summation yj sub j. Because of the linearity condition, we can write this as summation xi, the connection we are getting from moving y with respect to each basis. Everything else the same. Now, because of the linearity condition of the second thing, we can drive yj outside, and also using the definition of affine connection on the basis to another basis, we get exactly to this derivation, which is how much vector field I changes if I move along the vector field x. Okay. Let me for example, I can yes. We will get through all these calculation later. So I think if any of you have questions regarding the connection, now is a good point to ask. So affine connection is nothing but n to the power of 3 numbers, which define how I should change a vector field with respect to another. Okay. Is that clear for everyone? Okay. Now I want to talk about geodesics and its relationship with connections. So if you remember from the last session, we defined geodesic to be between the 2 points. So given 2 points, P and Q, the geodesic I will show with this is the curve with the least distance between the 2 points P and Q. And what is distance? As we discussed, is going to be so the distance is given by the essentially the inner product we are using with respect to the Riemannian metric. So the geodesic is essentially the least distance curve between 2 points. But this is not the only generalization of lines. So when you are in Euclidean space, what is the geodesic between the 2 points here, P and Q? It not only is the least distance curve, but there is also another intuition behind geodesic, which is the least curved curve. So there is no curvature in the line. So already we have two kind of different generalizations we can have for lines. Consider them first as the least distance curve between 2 points, or second, consider them the least curved curve between the 2 points. This is the two generalizations we can go. We already discussed about the geodesics with respect to Riemannian metric, which is given by this. But here, we're going to see how we can define curvature and what is the geodesics with respect to those curvatures. Okay. First of all, to define geodesic with respect to the curvature, we need to define curvature. We need to define movement of one vector field to another. And then it's very natural to define the least curved curve, as we'll see. Okay. Consider the following question. How can we move a vector from one point on a manifold to another in a way that it preserves the direction relative to manifolds geometry? So again, like the compass you have, you want to consider the path, how we can preserve the north direction. And this path and the north vector are dependent to each other. Take a look at this example. Consider Earth. You are on Earth, and essentially your compass is showing north. If I take this path, essentially you want your compass to show north. This is curve 1. So after taking curve 1 from P to Q, the north vector would look like this. But what if I take this other path? First coming over here, then coming down. Consider again glued north vector. So it would come up, and then as you come south, it would essentially showing south. So taking curve 2 of the north with respect to curve 2 instead of curve 1 would show you south. So we already have some intuition behind how we can generalize this viewpoint of changing the vector alongside curves. So the vector we get at the end would depend on the curve we took. And we want it to somehow be parallel at each point. Parallel in the sense that at each point, consider very small, very, very small steps you're taking. The north direction at each point you're getting is parallel in small step sense. Okay. Here is where our definition of affine connection would help us. So if you have a vector field at each point, which you can consider it as the northern direction, what you mean by autoparallel transport of that vector field alongside that curve is that the connection of changing with respect to the curve would be, the derivative would be 0, which, as I mentioned, is the same as considering it, if I take very small steps, to be 0 or parallel. So what does this mean? This vector field we get does not twist or does not rotate. It just goes as the direction of the curve. In the example here, if we took the C1 curve, as you can see, at each point, although the curve is going in the right direction, at each point, the vector we're getting is parallel to each other. And if we take the second one, also the vector we get at each point is parallel. So this definition would essentially give us the intuition we wanted to build upon. As you remember the connection, what does connection means? Connection means if I go alongside this vector field, which means if I go alongside the curve, how much my vector field would change. And we say if it is the case that it's 0 when we are considering an autoparallel curve. Now, if you remember, the whole idea of geodesic we were gonna think about was built upon the least curved or least twisted curve we can think of between 2 points instead of the least distance between 2 points. So we already have some kind of definition of the vector field moving alongside curves. Now let's see if we can define geodesics. Okay. Again, this is geodesics. We can so in order to solve this, so given a curve, what is the autoparallel transport of a vector field I have? So at each point I have. How can I solve this? If you use the definition of the affine connection, which is the linear function, you get to this equation where x at t is the point at curve at time t, and solving this is essentially solving a linear ODE system, which is everything is smooth, so there is the answer. So given any point and any curve, you can, given any vector, you can come up with the autoparallel transport of that vector. Okay. So we already know how to solve this. We're gonna ask ODE solver, and it's done. Now, I will go over all this after I define everything on the information geometry structure we have. So now we are ready to go for the geodesic. So we already know how we can calculate the north direction alongside any curve. We just need to have autoparallel condition. So how can we come up with the second intuition of the line, which was the least curved curvature? So if you think a little bit, you see what you need is that at each point, the vector you get of the tangent vector to your curve does not change as you go alongside the curve itself. So it is this definition that gives you the geodesic definition. Let's see why this thing works. So on a sphere again, consider 2 points, P and Q. We already know that the geodesic connecting the two with respect to the least amount of distance is the green one. Okay? Consider going alongside the green curve. At each point, this is gamma dot, and you are considering the connection between, yes, someone?
Hi, sorry, I had a question. So I got the intuition behind why we need a fine connection. If I'm right, what I got was that, for example, we want to have something that helps us if we're moving, for example, on Earth, we want something that we're holding to show upwards from a global perspective, so to the third viewer from outside. Is that correct? So the autoparallel part.
Mm-hmm. That's...
And my question is, I kind of lost the plot on how a fine connection is used to sort of give us that autoparallel condition?
Okay, I will discuss both in a minute. Thank you. This is a very good question. So the north direction is somewhat misleading. How come? As you saw in the definition of connection, we had freedom over n to the power of 3 things we could come up with different connections and connections. So it's not about a third observer view that can say, okay, I want all vectors to show north. Consider you are in a sphere, but you don't know where is north, where is south. So the space is not embedded in any space. So consider a sphere not as a sub Euclidean 3D space. Consider it as a sphere. All affine connection does is that I have a vector field, or I have a 2D space glued to point A, and I want to see how it would change if I go alongside that curve. So one affine connection would give you this one, but if you consider another affine connection, it would give you another thing. So it's not the importance of the invariance of upward. So in the second one, because the affine connection is changing north, although we are defining north in the second example as this point. So affine connection does not directly mean we need one north. It can have a lot of different interpretations. But if we consider affine connections with all the Christopher symbols equal to 0, but the northern one equal to 1, then essentially the affine connection would mean that, okay, I want to change the 2D space glued at each point in a way that always north in this 2D space remains the same. But we can come up with lots and lots of other affine connections that change that. So I want to emphasize on this. So given Riemannian geometry, Riemannian manifold M and G, we can come up with different affine connections. Actually, infinitely many affine connections. We haven't discussed the relationship between the Riemannian geometry we already discussed, the inner product, and its connection to the affine connection. So affine connection could be any linear function that does this thing, and everything is smooth. So you can smoothly change your glued 2D space to another 2D space smoothly, not with invariance of northern or southern pole or anything else. Each connection means one thing, but after this session, we'll see which one is more important and what is the relation. I haven't yet discussed the relationship between the affine connections and the Riemannian geometry. That's for the first question. Is that, did I answer your question?
Yes, thank you.
Okay. Now we go to the second one, which said, which the question was, I think here. So at each point, Vt is given by Vi So this is the definition of vector field at each point. And then we have the respective vector field. I will answer your question in a second. So affine connections, we given V with this, and gamma dot could be, again, gamma dot is in the space of all vector fields of a Riemannian space. So this is also given by gamma dot I. I would show it with J. So this is essentially what we are talking about. The affine connection, which I would later address it with connection, is gamma dot J of okay. Then we have the linearity. Consider connection because it's affine, so linear. This is the first component. This is the second component. So we can wrap it up and consider each individual. So it would give us summation over J, gamma dot J of this creature, and then VIT of XI. Okay. And then what was this? This was given by the Christopher symbols, which was essentially, if you consider this, this is nothing but the summation over yes. So if I take a look at this, this is essentially, if I put the summation to 0 and consider K, because if the whole thing gonna be 0, at each coordinate, it should be 0. So this is essentially exactly the upper one. So this is the ODE system we're gonna solve. Then the affine connection between 2 points are not unique, right? So affine connection, you should not consider it as a local operator. So given any manifold, I can come up with one connection which calculates how I should change the glued vector field, or I can come up with another, so regardless of each point. So affine connections are not unique, and based on points, they are not unique neither. Also, do they depend on the choice of coordinates? That's a very good question. We will see that we are just interested in those affine connections that are invariant on their the change of coordinates. And we'll see that the two geodesics we discussed last session are essentially related to the connections that are invariant on their change of coordinates. So no, in general, the affine connections are not independent of change of coordinates. So if I, instead of considering x1, x2, I consider x1, x2 squared as my new coordinate system, then the affine connection would change behavior in the two, all unless I consider a specific connections. Okay. Now we go for the geodesic. So we started the autoparallel transportation of a vector field. We considered it to be the one that if I move along the curve with respect to a connection, I would give the same vector field at the end. So now we change the vector field VT we saw with the vector field resulted by the curve itself. So between 2 points, P and Q, we can consider we can solve for this equation. Again, to solve this, we expand gamma dot T and we expand this too. And then we end up with this. Remember that this second order derivative comes from taking derivative of gamma dot with respect to gamma dot. So another name for connection, affine connection, is the covariate derivative of y with respect to x. So you can consider affine connection as some kind of derivation. It calculates the difference between y and x if I move along x. So if I solve this with respect to x at each time t, it would give me a curve. What curve? That it is parallel to itself. If I consider moving along the curve and I calculate the connection of the tangent vector, it would be 0. The intuition behind it is that this 0, which represented the being parallel of all vectors together, means that we are considering the least amount of curvature at each time t. So we are already generalizing the straightness of the concept line instead of the shortest path. So although the first geodesic we discussed was the geodesic with the least distance, here, if we define geodesic as the least curved curve or the straightest curve, then it's not unique. For example, in a sphere, again, between the 2 poles or between these 2 points, P and Q, if I have some natural connection, I will show you what is natural connection. The natural connections are those that are invariant with respect to change of the coordinates. It would give you not only this one, which is the shortest, but also the one that goes around the sphere and come to Q. So this is also a geodesic. So if we generalize the concept of line with respect to straightness, then geodesic would not mean the shortest path. It would mean the least curved path. And again, I want to emphasize on the following thing, that the Riemannian geometry has nothing to do with the connection. So given the connection, I can come up with a connection that this thing is the geodesic. Although it does not look straight, although it does not look shortest path, but I can come up with a concept of curvature, which is represented by affine connection, which is represented by the n to the power of 3 numbers of functions. I can come up with a connection that this thing would be the resulting geodesic. So we have one thing, which is our geometry, and then we have this connection. So the next question could be, what's the relationship between the connection and the geometry? So the concept of geodesic, is it clear? Okay. Okay. If you remember from calculus 1, the concept of curvature was very closely related to the second derivative. And as we discussed, connection, any affine connection, the other name for affine connection is covariant derivative. So if we take a look at the second covariant derivative of one vector field with respect to another, we would essentially get the same understanding of the curvature. There are thousands of different intuition behind curvature, which give rise to the same curvature tensor R here. I motivate all of you to go and search about different understanding of the curvature. For example, if you remember Gaussian curvature, it represents the amount of change of measure between the first Euclidean space and our manifold, and the change of each cube would represent the curvature at each point. That was the Gaussian curvature. There is also Ricci curvature, which consider all curves going alongside each point and calculating the change of those curves at each point. So in a sense, curvature wants to calculate the change, but not in the first order, but second order Taylor expansion of the space. So that's what we mean by curvature. Okay. The definition of curvature, we won't work with this a lot. We won't apply this to anything, just to show you that Riemannian geometry and differential geometry is so complicated to calculate everything explicitly, is given by the following. So given 3 vector fields, each of them is given by xi, this by j, this by k. Then at each point, it would be a linear, again, a tensor. We want it to be linear with respect to first, second, and third components. So it's given by this form of this number of functions. Yes. So what does this actually mean? Again, consider changing. So we have three vector fields. This is a little hard to show intuitively, but the whole intuition comes with the second derivative. So we want to approximate curvature with second derivative of a function, and that would give rise to a linear function. But to show it here, consider this as P and consider this as Q. I have 3 X, Y, Z. I have 3 smooth vector fields glued at each point. So if I change my point P, the 3 points would change as well. Then this is what curvature locally at each point P calculates. If I change Z with respect to Y and then change it to X, it's like going into this direction. Maybe it's better to show it with another color. So this is the first vector. Or I would change Z with respect to X first and then Y. Or I would change Z to the resultant of some, this is the Lie bracket between X and Y. We don't need to dive into it. With respect to some some multiplication of the two vector fields. If I look at these 3 vectors, so again, when I'm considering connection, it means derivative. So I'm changing Z with respect to Y a little, then with respect to X. So when I get to X, it means I have gone through YX. So why does it this show curvature? Consider this torus, very narrow torus. If I start from here, if the vector X would represent the inner circle instead of the outer big circle, if I look at the change of Z with respect to that, it would be a lot. So why? Because there is a lot of curvature alongside that. But if I go with respect to Y at first and then X, then that is also a lot. But this thing would cancel out the second one. So this would be much larger and would show the large curvature locally. I hope I gave enough intuition behind this complicated definition of curvature. But again, at each point, so it's better to define curvature. So curvature of each point with respect to the affine connection I have is defined. So again, if I change the affine connection, the curvature would change. So it's not about considering the space as a space embedded in another n-dimensional space. With this affine connection, with considering different affine connection, you're going to get different curvature. But if you remember from the first session, we also defined the curvature with respect to the second derivative of our inner product. So we hope that the two definitions with a good definition with a good affine connection, the two definition would be the same. But this curvature tensor has nothing to do with the geometry yet. Okay. This is the curvature, and then we need to consider the connection between affine connections, the relationship between affine connections and the geometry itself. So we have a Riemannian metric, which in information geometry would be Fisher metric, which let us measure length, angles, and distances. And a connection tells us how to compare or transport vectors across different points. So how can we connect these two? One way of thinking that is that we are interested in those connections. Consider I have again a manifold here. I have a point P and I have another point Q. So I have two vectors here. And with the affine connection, VW, I can get to V prime and W prime. What essentially we call good is that the angle between them before moving them autoparallel to other point is invariant. So that's something we can formulate later, but G of P of V and W be the same as the inner product between the 2 points, considering the autoparallel of P and Q of V and moving the W autoparallel to the point Q with respect to the connection. What is this? This is nothing but V prime. This is nothing but W prime. So that's what we're looking for. Out of all connections, the one is important for us that have this kind of relation. So to formulate that, again, because the affine connection is n to the power of 3, so we need n to the power of 3 constraints. So we need n to the power of 3 number of vector fields, each of them having n. What it says is that essentially we want this condition of invariance of the angle to be preserved. And we call the respective affine connection Levi-Civita of the Riemannian metric. So starting from a Riemannian metric G of a Riemannian space M, we get to the affine connection of Levi, normally they call it LC, this connection. And because of this constraint, one can see that the straight geodesic with respect to Levi-Civita geodesics would coincide with the shortest path. The curvature would be the same, everything would be the same. So we started from the concept of changing the vector fields, and we got to the same concept of inner product. Okay, Is this clear, the connection between the inner product and our connection? Okay. Okay. Now, as you saw, we started from a very arbitrary connection, and then we had already, so given your Riemannian manifold and your connection, and of course you have G. But this connection might not satisfy this condition. What can we do here? So one idea is to rewrite this as this, but with a slightly different connection. We call this a dual connection. So starting from a connection, Riemannian metric, you calculate the dual connection represented by the star here, such that it satisfies the same, but instead of the connection, we have dual connection in the right-hand side. So what does it mean intuitively? So the connection calculates moving from x to y. So x, y calculates the, or take the derivatives with respect to x of y, but the dual one somehow do the inverse thing of calculating the derivative or another derivative of y with respect to x. We would see, I think, I don't have enough time in this session, why we call this dual. This is, we will see it. This is essentially the same Legendre transform of a function, which we call it dual. We'll see that it coincides with that. But for now, the things we learned in this session are that we start with a connection and a Riemannian metric, and we end up with another dual connection. The question might someone ask is that why to consider connections other than Levi-Civita connection? We will see that in information geometry, the paths we took last session between 2 points, some of them were the least loss of information path, which coincides with the KL divergence. And another one was the optimal transport path. Both of them would correspond to geodesics that are not the shortest path geodesic, but are straightest geodesics, which I would calculate in the next session. So that's the idea of connection and the dual connection. Just to give you a taste of what this means, if you remember correctly, we started with the parameterization of the normal distribution with this. We saw that if we consider a gradient descent on this one, it would give rise to the optimal trajectory path of optimizing MLE. And if we consider this, it would optimize the Wasserstein distance. The path would look like transporting the normal distribution iteratively. As we will see, the first path, which is called E coordinates, would coincide with the geodesics with the connection of log of likelihood, and the second ones would coincide with the geodesic path of the connection of likelihood itself. And more surprisingly, both of them are geodesics, and so the connection with this to our first one is that Fisher metric makes these two dual. Okay, one might ask, why do we care? Because as we see, because of the whole convex function optimization and everything, because you have dual spaces, this has a lot of applications. To name one, I have mirror descent, which I would discuss next session, that having this duality would help you to optimize the whole parameter with better algorithms like mirror descents instead of descent itself. And also it has very straight applications in reinforcement learning. If we are considering policy optimization algorithms, one vanilla gradient ascent is as following. But considering mirror descent on this, which is considering the geodesic path, because if you're not familiar with reinforcement learning, forget about this section. But if you are familiar with reinforcement learning, you know that log of the policy is most of the time used in the reinforcement learning. And with the dual thing we already developed, we can come up with algorithms that leverage this tool. And already TRPO and natural policy gradients leverage this duality. So the applications of building this duality, the connection between affine connection, dual affine connection, and the geometry of Riemannian space itself would give rise to a lot of optimization, faster optimization techniques. I hope I did not dive into the details of every definition. I just wanted to keep everything very intuitional, because what we do after the next session is that we just use libraries of Python, which already can calculate the curvature, the geodesics, and everything. So we just need some intuitional understanding of the whole concepts. But I would emphasize on going and reading further into the mathematics of both differential geometry and Riemannian geometry, if anyone is interested. And yes, if you guys have any questions, I would be more than happy to help. Mm-hmm. Okay, so we already discussed a lot of essentials of Riemannian geometry in this session. In the next session, we would discuss what all connections and different kind of connections play a role in information geometry. We would see the EM algorithm we discussed in the first of this session solved with these two kind of dual connections. And hopefully we are done with the essentials of information geometry. And in the last two sessions, we would first go for the machine learning understanding, the applications of information geometry in machine learning. And lastly, we would go with the very hot and new subject of leveraging information geometry on financial mathematics. Okay. Thank you, everyone. See you next week, Wednesday at 5:30.